This is Chapter 17 of Astronomy 100. This is called The Birth of the Universe. So the first section we're going to look at is the Big Bang Theory. The goals today are what were conditions like in the early universe and how did the early universe change with time. As far as the conditions early in the universe, we're looking at things that are highly debatable. They can be argued in many different ways because of the nature of the particles and the energy that we're dealing with. Obviously, no one was there to observe these conditions, so we're speculating quite a bit on what those conditions were like. But it's interesting to do the speculation because by doing it, we understand a lot more about matter and energy. We don't know everything about those two entities, so we can sort of guess, speculate, hypothesize on what the early universe was like in dealing with those two things. So what were conditions like in the early universe? This is sort of a map of the cosmic microwave background radiation that we see in pretty much all directions around us. It exemplifies what we think is the remaining radiation from the original explosion, the original Big Bang. The early universe was probably very hot and very dense, as we can see from this graph, going backwards in time to 10 to the minus 45th seconds since the Big Bang. Temperatures were extremely, extremely hot. This is, again, a guess as to what we think the universe started out as, not only in space but also in time. So that today we have, based on this graph, an idea of what we think the remaining or residual temperature of the universe would be. Early in the Big Bang, there was not only particle creation, but particle annihilation. As we know from the equation over on the right, E equals mc squared, that photons could be converted into particles and antiparticles, and vice versa. And in the same respect, electrons and anti-electrons could form photons. So mass and energy were invertible or convertible in the early stages of the Big Bang because of the temperatures. So how did the early universe change with time? Well, the earliest eras are defined by the kinds of forces present in the universe. Early on, there was basically just one force, and as things cooled down and expanded, eventually energy was being converted to particles, and those particles are what we know of today as atoms. So here's what we think the universe consists of. 4 known forces: strong force, electromagnetism, which we know about, the weak force, and of course gravity. So as you can see by the timeline here, going backwards from right to left, there's what some scientists call a superforce, and this is where string theory is being developed, where different ideas are coming about, where early in the formation of the universe there was this just one superforce. And then we have 2 forces, grand unifying theory force and gravity separating, and the gut force or GUT force dividing up into the strong electromagnetic and weak forces as time went by. So going backwards in time to the superforce, the question is, do forces unify at high temperatures? We think so, because we have the electric force, we have the GUT or grand unified theory force, and at the beginning we have string theory. So if these particles, these pieces of matter, were so hot and so dense at one time, they were one force. This is a timeline of things that we think happened as the universe progressed We have different eras on the left where the different forces are separating out and eventually into different types of matter. And over on the right, the different temperatures at which they occurred. So again, going back to the initial period after the Big Bang, we have what's called the Planck era, where all forces may have been unified. Then we have the grand unifying force, the Gut era, where temperatures were slightly lower, time had progressed, and this is where gravity became distinct from other forces. So that's really what to remember about the Gut era, is that gravity separated from the other three forces. And then the electroweak era, where after a certain amount of time, and again progressively cooler temperatures, gravity became distinct from the other forces, but there are still the strong, the weak, and the electromagnetic forces may have been unified at that ending. Then we have the particle era, where things are cooled down enough and enough time has progressed that amounts of matter and antimatter are nearly equal. But look at this in parentheses. There's roughly one extra proton for every 10 to the ninth, or 1 billion protons, to have proton-antiproton pairs. So in other words, there was roughly one extra normal proton for every billion proton and antiproton pairs. So protons had a slight edge on the antiproton numbers. And then the era of nucleosynthesis, where it began when matter annihilates remaining antimatter, and matter is the dominant entity at that time, and nuclei begin to fuse. So a proton and an electron, or two protons and two neutrons, would come together and form a certain nucleus. The era of nuclei, where again after about 5 minutes in this time scale to 380,000 years after the Big Bang, temperatures have decreased again, helium nuclei form in about 3 minutes, and the universe becomes too cool to blast helium apart. So in other words, the helium nucleus remains intact. And of course the era of atoms, where after as much as 1 billion years, temperatures are cool enough, atoms have formed, and the remaining background radiation is released. So we have atoms forming after about 380,000 years after the Big Bang. And then the era of galaxies, which we know of today. The temperatures are fairly cool or cooler than the other eras, and this time goes from 1 billion years to the present. So during this time, the first stars formed and galaxies formed by about 1 billion years after the Big Bang. So that would mean if the universe is about 14 billion years old, then we actually had stars and galaxies at about a 13 billion year time scale. So what were conditions like in the early universe? Well, it was so hot and so dense that radiation was constantly producing particle and antiparticle pairs and vice versa. How did it change with time? Well, as the universe cooled, particle production stopped, leaving matter instead of antimatter. Remember, there was only a slight imbalance toward the protons when we're dealing with the difference between matter and antimatter. And fusion turned the remaining neutrons into helium. Radiation traveled freely after the formation of those atoms. So, what's the evidence for the Big Bang? Well, our goals here are how do observations of the cosmic microwave background support the Big Bang theory, and how do the abundances of elements support the Big Bang theory? So we've detected leftover radiation from the Big Bang, and as you can see in your book, two gentlemen, as you see in the upper left there on page 446, Penzias and Wilson, they basically discovered that radiation existed in pretty much all directions. Also, the Big Bang theory correctly predicts the abundance of helium and other light elements in the universe. So, how do observations of the cosmic microwave background support the Big Bang theory? Here are the two gentlemen that discovered that radiation left over. in 1965. They basically were cleaning a radio telescope. That's what you see in the background, where they, after cleaning the telescope, realized that there was still static or background noise that they were detecting in all directions. So background radiation from the Big Bang has been apparently streaming across the universe since atoms formed at temperatures of at or less than 3000 K, which would be in the visible part or the infrared part of the electromagnetic spectrum. So as you see here in the orange and the blue areas, we have the era of nuclei on the left and then the era of atoms on the right. So we would be, or our time scale would be going from left to right into cooler and cooler temperatures. The expansion of the universe has apparently redshifted this thermal radiation so that we have something 1,000 times longer, and now we're in the microwave part of the electromagnetic spectrum. So the background radiation has this perfect thermal radiation spectrum, and it apparently has an ideal temperature of a little less than 3 kelvins. So obviously from the Big Bang, which would have been a very, very high temperature, down to 3 kelvins, we can estimate how long that took. And then we have this satellite called the Planck satellite, which you see the exact same picture on page 447. It gives us detailed baby pictures of structures in the universe. In other words, if these are stars and galaxies, we see that the overall structure is fairly uniform. So how did the abundances of elements support the Big Bang theory? Well, we have these helium nuclei being synthesized, and of course that requires 2 protons and 2 neutrons. The destruction or the annihilation of protons fusing into these helium atoms give us some kind of a ratio here that lets us see just how that helium quantity would change through time. So protons and neutrons combined to make this long-lasting helium nuclei when the universe was approximately 5 minutes old. So how do observations of the background radiation support the Big Bang theory? Well, radiation left over from the Big Bang is now in the form of microwaves, the microwave background, which we can observe with a radio telescope. And then how do the abundances of elements support the Big Bang theory? Observations of helium and other light elements agree with predictions for fusion in the Big Bang theory. So in other words, as the universe cooled, more and more of this helium could form, and we have a rough idea of just how quickly it can form as temperatures cool. So what key features of the universe are explained by this thing called inflation? Well, it may seem hard to visualize, except this diagram shows it pretty well at the top of page 451. We can have inflation make structures by stretching tiny quantum ripples to enormous sizes. In other words, there might be small irregularities, but as inflation occurs or as expansion occurs, these ripples in density then become the seeds for all the structures in the universe. So as the density decreases, the smaller clumps of matter can actually form stars and galaxies. This is what we think is a good comparison of the overall geometry of the universe, and it's related to the density of the matter and the energy in it. So if we have a flat geometry, then things are pretty evenly spaced. If the density of the universe is greater than what's called critical, then maybe the universe has a spherical geometry. And if the density is less than critical, then we have what's called an open geometry, in which case there would be kind of no beginning or no end. We would continually move within the universe. So this idea of inflation is kind of like an ant on a balloon, whereas the balloon increases in size, the roundness or the sphericalness of the explosion decreases. So it flattens the overall geometry, like the inflation of a balloon, causing the overall density of matter plus energy to be very close to what we call the critical density. So, did inflation really occur? Well, we can look at temperature differences in the angular separation in the sky, and we see that that's maybe about 1 degree. So the patterns of structure observed by the Planck satellite shows us basically the seeds of the universe. This is where matter has been expanding out with a very small separation between the pieces of matter, such as galaxies. Observed patterns of structure in the universe agree with seeds that inflation would produce. So if we use that balloon analogy to describe how the matter expanded out in all directions, this idea of inflation seems to fit. So what key features of the universe are explained by inflation? Well, the origin of the structure, the smoothness, the near critical density of the universe can be explained. The structure may come from inflated quantum ripples, in other words, galaxies forming from more dense areas early on in the Big Bang. And the observable universe becomes smooth before inflation when it was very tiny. Also, inflation flattened the curvature of space, bringing the expansion rate into balance with the overall density of mass and energy. So the expansion of the universe seems to be fairly uniform. There's no one area which is more dense than the other. So why is the darkness of the night sky evidence for the Big Bang? Well, look at the difference between A and B in this picture. And I think you have it also on page 455. If you had a large forest and the trees were very, very dense, you would not be able to see clear sky or blue sky behind it. But in a smaller forest with a smaller number of trees, you do see some open spaces. So how does this compare to what we see in the night sky? Well, there's something called Olber's paradox. If the universe was infinite and unchanging and everywhere the same, then stars would cover the night sky. In other words, we'd be blinded by the night sky simply because there would be no empty space, no dark space in the sky. But is that the case? Obviously not. This is what we would be looking at in this forest then, would be an unending line of trees. But the night sky is dark because the universe changes with time. And as we look out into space, we can look back to a time when there were no stars. So in other words, we can look at the near trees, we can look at the far trees, but beyond that, we can look at a time and a place in the universe when there were no stars. So the night sky is dark because the universe changes with time, and as we look into space, we can look back to a time when there were no stars. So this would lead us to conclude that the universe is finite, or at least what we can see of it. There's only a definite number of stars and galaxies. So why is the darkness of the night sky evidence for the Big Bang? Well, if the universe was eternal, unchanging, and everywhere the same, the night sky would be covered with stars. But the night sky is dark because we can see back to a time when there were no stars.